Welcome to today's deep dive. We are so glad you are joining us.
Yeah, absolutely. Thanks for tuning in.
Today, we are looking at something that surrounds you every single minute of every single day.
Even though you probably never even notice it.
Exactly. We are digging into an incredibly extensive 500-question training text for the Advanced Diploma in Industrial Safety.
Which I know sounds a bit heavy at first glance.
Right, I know what you might be thinking. A 500-question safety compliance document.
Yeah, it sounds like a cure for insomnia.
But stick with us, because our mission today is to completely decode this invisible, highly engineered rulebook that literally keeps you alive.
It really is a survival guide when you break it down.
We are going to translate what looks like dense compliance text into a fascinating survival guide for the modern world. You are going to see exactly how experts quantify, calculate, and ultimately control danger.
Because danger is everywhere, mathematically speaking.
Have you ever wondered why a near miss at work where nothing actually happened and no one got hurt is treated as a massive deal?
Oh, it's a huge deal.
Or why water, the thing we all instinctively associate with putting out fires, is actually the absolute worst thing you can throw on certain types of blazes?
It can literally make things explode.
We are going to get into all of that today.
Oh,
Okay, let's unpack this, starting right at the foundation. How do we even define what a threat is?
that is the perfect place to start.
Because early on, this text makes a massive distinction between two words I honestly always used interchangeably: hazard and risk.
It's a really common misconception, honestly, but that distinction is the absolute cornerstone of all safety engineering.
Really? Just those two words?
Yeah, a hazard is defined as any source, situation, or act that has the potential to cause harm. It is the thing itself.
Okay.
Risk, on the other hand, is the likelihood that the hazard will actually cause harm, combined with the severity of that harm.
I was trying to wrap my head around this, and the easiest way I can picture it was with a shark.
Oh, I like that.
Yeah. So a shark swimming in the ocean is a hazard. It has the inherent potential to cause you a lot of harm.
Definitely.
But if you're standing completely safely on the beach in dry sand, your risk is zero.
Right, because there's no exposure.
Exactly. The risk only comes into play when you decide to go swimming with the shark. The hazard hasn't changed at all. It is still a shark.
But your exposure to it has changed.
Right, which drastically increases the risk.
That is a perfect way to visualize it. What's fascinating here is how this basic understanding of risk leads to a broader mathematical reality of how accidents actually happen in the real world.
The math behind the accidents.
Exactly. And this brings us to a concept known as Heinrich's triangle, or the accident triangle.
I saw this in the text.
It's a theory that models the statistical relationship between different types of incidents, and the ratio is incredibly specific. It's 1 to 29 to 300.
I stared at that ratio for a long time. 1 to 29 to 300.
Yeah.
What does that actually look like for someone working on a factory floor or, say, a construction site?
Think of it as a historical trail of breadcrumbs leading up to a disaster. For every one major severe injury that happens in a workplace, there will have been 29 minor injuries preceding it.
So 29 smaller warnings.
Yes. And preceding those 29 minor injuries, there will have been 300 near misses.
300.
300. And a near miss is an unplanned event that didn't result in injury or damage, but absolutely had the potential to do so.
Give me an example of that.
Say a heavy wrench falls off a scaffolding and hits the ground right next to someone's foot. Nobody is hurt. Nothing is broken.
That is close.
Very close. That is a near miss.
Wait, so if I trip over an extension cord in the office, but I catch my balance and I don't fall, that's a near miss.
Absolutely.
And the idea is that if you ignore 300 of those trips, eventually someone is going to break their arm.
Precisely the point. If you just ignore the near misses because, no one got hurt, you are essentially just ticking down the clock until you hit that number 1.
The major catastrophic injury.
Right. In the safety world, understanding this shifts an organization from being reactive to being proactive.
Which makes sense. You want to catch the 300, not the 1.
Exactly. It's the difference between tracking what they call lagging indicators versus leading indicators.
I have actually heard those terms thrown around in business before. A lagging indicator is basically looking in the rearview mirror, right?
Yes, exactly. Lagging indicators track safety performance after incidents have already occurred.
Like tracking injuries.
Right. You are looking at your injury rates or how many workdays were lost to accidents. It tells you that your system has already failed.
Too late to fix it for that person.
Exactly. Leading indicators, however, are proactive. These are things that predict and prevent incidents before they occur.
So that would be the near misses.
Yes. Tracking the number of near-miss reports submitted or looking at how many hazard inspections were completed this month.
So if you only look at lagging indicators, you're basically waiting for someone to get hurt to find out if your safety rules are working.
Which is a terrible strategy.
Which brings us to how we actually stop those hazards. The text outlines something called the hierarchy of controls, ranking safety measures from best to worst.
This is a really crucial part of the manual.
I am not going to lie, this completely blew my mind. Personal protective equipment, or PPE, things like hard hats, safety glasses, and gloves, is ranked as the absolute least effective control measure.
The very bottom of the list.
It is literally at the bottom. I always thought a hard hat was the ultimate safety gear.
It seems so counterintuitive, doesn't it? Because PPE is the most visible part of safety.
Right, when you walk onto a job site, the first thing they hand you is a hard hat and a high-vis vest.
Exactly. But logically, if you think about it, PPE doesn't remove the hazard at all.
It just sits there.
It just puts a tiny physical barrier between you and the hazard. If that barrier fails, or if it doesn't fit right, or if the worker forgets to put it on,
The injury happens.
the injury happens.
So what is at the top of the list?
The most effective approach is elimination. Physically removing the hazard entirely.
Like getting rid of a problem machine.
Yes. If you have a loud, dangerous machine, getting rid of the machine is the best safety measure.
But you can't always do that.
Right, so if you can't eliminate it, you use substitution, replacing the hazard with something less dangerous.
Like using a non-toxic chemical instead of a highly toxic one.
Exactly. Then you drop down to engineering controls, which means physically isolating people from the hazard.
Oh, like putting a heavy soundproof box over that loud machine.
Perfect example. Then below that are administrative controls, which means changing the way people work.
Like rotating shifts.
Yeah, rotating shifts so no one is exposed to the noise for too long.
And then finally the hard hat.
Right. Only after you have exhausted all of those do you hand someone a pair of earplugs. That is your PPE, your absolute last line of defense.
It makes total sense when you lay it out like that.
Mm-hmm.
Giving someone earplugs is basically admitting we couldn't fix the loud machine, so hopefully these foam squishies work.
Pretty much, yeah.
Speaking of things you can't just slap a hard hat on, let's talk about fire.
Oh, fire dynamics are fascinating.
We all learned about the fire triangle in school, right? Fuel, oxygen, and heat.
The classic model.
But reading through this material, they update this classic model to something called the fire tetrahedron. They add a fourth crucial element, the chemical chain reaction.
That chemical chain reaction is what actually sustains the fire once it has ignited.
Okay.
And understanding this is why water is absolutely not a universal solution for putting out fires.
Because it doesn't stop the reaction.
Exactly. The text breaks fires down into different classes. Class A fires are your ordinary combustibles: wood, paper, cloth.
And water works fine there.
Water works beautifully there by absorbing the heat. But then you have Class B fires, which involve flammable liquids like oil or gasoline.
Right, and if you throw water on a grease fire in your kitchen, it doesn't put it out, it explodes.
Because water is heavier than oil.
Oh, right.
The water sinks below the burning liquid, rapidly heats up, and instantly boils into steam.
Which takes up more space.
A lot more space. That steam expands violently and throws flaming oil all over the room.
That is terrifying.
It is. And then you have Class C fires, which are electrical.
So no water there either.
If you spray a hose at a live electrical panel, the water conducts the electricity right back up the stream to you.
Oh, wow.
For those types of fires, you need extinguishers like CO2 or dry chemicals that actually interrupt that fourth element, the chemical chain reaction, or smother the oxygen.
The section on fire dynamics goes into some truly terrifying scenarios of what happens when fires behave unpredictably in enclosed spaces.
Enclosed spaces change everything.
They describe three extreme phenomena.
Yeah.
First is a flashover. And this isn't just a fire spreading from a couch to a rug.
No, not at
A
all.
flashover is a rapid thermal transition where every single combustible piece of material in an enclosed room
Mm.
simultaneously ignites.
Yes.
The room doesn't just have a fire in it. The entire room becomes on fire all at once.
Because the ambient heat reaches the ignition temperature of everything in the room.
That's crazy. Then there is a backdraft. We have all seen this in the movies, where the firefighter touches a hot door.
Classic movie trope, but very real. A backtrack happens when a fire has consumed most of the available oxygen in a sealed room.
So it kind of dies down.
The flames might die down, yeah, and the fire's just smoldering, starving for air, but the heat is still incredibly intense.
Waiting for oxygen.
Exactly. If someone opens a door or breaks a window, fresh oxygen rapidly rushes into that superheated, fuel-rich environment, and the result is a massive, violent explosion pushing out of that opening.
Just a wall of fire. And then there's the BLEVE. BLEVE. Boiling liquid expanding vapor explosion.
This is perhaps the most devastating industrial fire phenomenon.
How does that happen?
Imagine a large sealed tank holding a pressurized liquid like propane. Now imagine a fire starts underneath or next to that tank.
So it's heating up the tank.
Heating it up. The fire heats the liquid inside far beyond its normal boiling point, but because it's in a pressurized sealed vessel, it can't actually boil.
Right, the pressure keeps the liquid.
Yes. The metal of the tank eventually weakens from the heat and fails.
And it cracks.
It ruptures. The pressure drops instantly to atmospheric levels. In a fraction of a second, all of that superheated liquid violently flashes into vapor, expanding to hundreds of times its volume,
Which creates the explosion.
creating a catastrophic explosion and often a massive fireball.
Okay, here's where it gets really interesting. We go from the massive, explosive, visible power of fire to a completely silent, invisible danger electricity.
Silent but incredibly deadly.
The text introduces a concept called the let-go current.
It is a profoundly chilling concept.
It really is.
The let-go current is defined as the yes. If you grab a live wire, your hand will automatically clench tightly around it.
And the number they attach to this let-go threshold is staggering. 6 to 10 milliamperes.
A tiny amount.
That is a microscopic amount of electricity. A standard household nightlight pulls more current than that.
It doesn't take much.
If you get hit with more than 10 milliamps, it doesn't matter how strong you are, your brain physically cannot tell your hand to let go. You are locked on to the source of the shock.
It highlights just how fragile the human body really is against engineered power.
Fiercely.
And the text makes a crucial distinction here between AC, alternating current, and DC, direct current.
Most people assume they are equally dangerous.
Right, but AC is generally considered much more lethal at equivalent voltages.
Why is that?
Because alternating current reverses direction constantly, like 60 times a second in a typical wall outlet. It causes sustained, violent muscular contraction.
Oh, because of the frequency.
Yes. This deeply disrupts the heart's electrical system, greatly increasing the likelihood of ventricular fibrillation, which is a fatal heart rhythm disorder.
And what's the threshold for that?
That fatal fibrillation can happen at just 100 to 200 milliamperes.
Electricity is terrifying because you can't see it till it's too late. But it's not the only invisible hazard out there.
No, definitely not.
It turns out the very air you breathe can become a weapon if you step into the wrong kind of room. Let's talk about confined spaces.
A huge topic in industrial safety.
I always thought a confined space was just a really small closet or a crawl space, but the definition they use is much more specific.
It has legal and safety implications, yeah.
It has to be large enough for a worker to enter, have limited means of entry or exit, and crucially, it is not designed for continuous human occupancy.
Right.
We are talking about inside storage tanks, grain silos, or underground utility vaults.
And the primary hazards inside those spaces aren't just getting stuck, they are atmospheric.
The air itself.
You are dealing with oxygen deficiency or the silent buildup of toxic or flammable gases. You can't see them, and often you can't smell them.
So you wouldn't even know.
Someone might go into a tank to clean it, breathe in hydrogen sulfide, and instantly pass out.
And human instinct is that a coworker sees them pass out, rushes in to save them, and then they pass out too.
Exactly. It causes a cascade of fatalities. This happens all the time if protocols aren't followed.
That's heartbreaking.
This is why the safety protocols are so incredibly rigid. You are required to have continuous atmospheric testing, a monitor constantly sampling the air while the worker is inside.
And someone has to stay outside, right?
Yes, you absolutely must have an outside standby person, often called a hole watch.
Whole watch.
Their sole responsibility is to stand outside the space, monitor the person inside, and initiate a mechanical rescue, like winching them out with a harness without ever entering the space themselves.
Never go in.
Never.
Speaking of toxic gases, I was reading the section on chemical exposure, and I figured breathing hazardous stuff in or swallowing it were the main dangers.
Those are common, sure.
But there are 4 routes chemicals enter the body: inhalation, ingestion, skin absorption, and injection.
Skin absorption is the one that catches people off guard.
Skin absorption really surprised me. Just touching certain chemicals can introduce them straight into your bloodstream.
Bypassing your lungs and digestive system completely.
And they break toxicity down into acute versus chronic. Acute is obvious. You spill acid on your arm, you see an immediate, severe reaction.
You know that's instant.
But chronic toxicity seems so much harder to track.
Chronic toxicity is insidious. These are the adverse health effects that result from low-level, long-term exposure over months or years.
Like dust.
Yeah, a worker might be inhaling microscopic silica dust every day. They feel fine on Tuesday. They feel fine next month.
But then years later,
10 years down the line, they develop a debilitating occupational lung disease.
to manage all these crazy chemical risks globally, the text points to the GHS, the globally harmonized system of classification and labeling of chemicals.
It's an incredible system.
And this is honestly brilliant design. Instead of relying on warning labels written in English, Spanish, Mandarin, or whatever local language, the GHS uses a system of 9 universal pictograms.
Which is so important in a globalized workforce.
Right.
It creates a visual language of danger that completely transcends language barriers or literacy levels.
That's the pictures you see on the backs of trucks.
Exactly. If you are handling a barrel in a warehouse anywhere on Earth, and you see the exploding bomb pictogram or the skull and crossbones, you instantly understand that the contents are severely hazardous.
You don't need to read the fine print to know you need to be careful.
You know immediately.
That universal visual design bridges perfectly into our next theme: man versus machine.
The physical hazards.
When you read the sections on machine guarding, the terminology alone makes you want to stand 10 feet back from anything with a motor.
It's very descriptive.
They describe mechanical hazards using incredibly visceral words. Nip points, which is where 2 rotating gears or rollers meet and can pull your hand in.
Right.
Shearing hazards, crushing hazards, and drawing in hazards.
The physical forces involved in industrial machinery are completely unforgiving.
They really don't care.
A machine doesn't know the difference between a piece of steel and a human arm. That is why one of the most rigorously enforced life-saving procedures in this entire industry is LOTO, which stands for lockout, tagout.
Wait, so lockout tag, is that just pulling the plug or throwing a padlock on a switch so nobody accidentally turns a machine on while a mechanic has their hands inside the gears?
That is part of it, yes. But if we connect this to the bigger picture, it is vastly more complex than just cutting the power.
Okay, how so?
The real danger highlighted in the text is stored or residual energy.
Stored energy.
Think of a shaken-up soda can. You haven't opened it yet, the can is just sitting there doing nothing, but there is immense pressurized energy trapped inside.
Oh, and if you open it, it sprays everywhere.
If you puncture it, it explodes. Industrial machines are exactly the same.
So even if you completely disconnect it from the electricity, the machine can still kill you.
Absolutely. A massive hydraulic press might be turned off, but there could be thousands of pounds of pressurized fluid still trapped in the lines.
Waiting to release.
Or a huge metal stamping arm might be suspended in the air, held up by a mechanical brake.
And if the brake fails?
If that brake slips, gravity takes over, power or no power.
Wow.
There might be massive compressed springs under tension or electrical capacitors that hold a lethal charge for days after being unplugged.
So LOTO handles all of that.
A LOTO requires that every single source of stored energy be systematically dissipated, blocked, or restrained before a human being ever touches that machine.
It really makes you realize that turning something off absolutely does not mean it is safe.
Not even close.
There are also some incredibly practical rules of thumb in here, particularly for construction safety. Take ladders, for example.
Oh, ladders.
I am guilty of violating this every weekend. The manual mandates the 4-to-1 ladder angle rule.
It's a classic rule.
For every 4 units of height you are climbing, The base of the ladder has to be placed exactly 1 unit away from the wall.
to prevent it from slipping out or tipping backward.
And when you are climbing, you must use the 3-point contact rule. You have to maintain contact with the ladder using either 2 hands and 1 foot or 2 feet and 1 hand at all times.
Always 3 points of contact.
Meanwhile, I'm usually walking up a ladder holding a cup of coffee in one hand and a power drill in the other.
You and millions of others, honestly. But those simple rules are actually engineered solutions to complex physics problems involving center of gravity, leverage, and friction.
Which leads us perfectly to the final overarching theme, the system of survival.
The big picture.
How do you scale these highly specific rules up to protect thousands of workers across different continents?
It takes a massive management framework.
The industry uses EHS management systems, environment, health, and safety. They reference the international standard ISO 45701.
Right.
And the engine driving these systems is the PDCA cycle plan, do, check, act.
It is a relentless, never-ending loop. You plan your safety objectives, you do the implementation, you check the results to see if they worked, and you act to improve the system for the next cycle.
So what does this all mean for the bottom line? Because implementing all of this sounds incredibly expensive.
It does seem that way up front.
But one of the most revealing parts of this entire dive was seeing how safety is positioned not just as a moral obligation, but as a highly calculated financial strategy. They have an actual mathematical formula to prove that safety makes them money.
It absolutely does. Companies track the ROI, the return on investment, of safety protocols.
They can actually measure it.
They measure financial benefits through drastically reduced workers' compensation insurance costs, lower regulatory fines, and a drop in their LTIFR.
LTIFR, lost time injury frequency rate. Basically, calculating how often people get hurt enough to actually miss work per million hours worked.
Right. And a lower LTIFR directly correlates to an increase in overall productivity and profit.
Because people are actually at work.
Keeping workers safe keeps the business running. But none of these systems or metrics mean anything without a genuine safety culture.
A safety culture.
A true safety culture relies on engineers creating fail-safe designs.
Like the dead man switch on a lawnmower.
Exactly. A fail-safe design means that if a system or a component breaks, it is mechanically engineered to default to a safe condition rather than a hazardous one.
Oh, so if you let go of the lawnmower handle, the engine cuts out immediately.
Yes, the failure mode is safe. And a strong safety culture actively fights against human nature, specifically the temptation to bypass these protections just to get a job done faster.
Which people do all the time.
Deliberately overriding a safety interlock or removing a machine guard is treated as the ultimate failure of safety culture.
Because you're inviting the risk back in.
Exactly.
It really changes how you look at the world around you. To recap our journey today, we have seen how deeply layered the mechanics of survival actually are.
It is a totally different perspective.
We started with the shark analogy, learning the difference between a hazard and a risk. We saw the historical breadcrumbs of the 1 to 29 to 300 accident ratio.
The near misses.
Right. We learned that the hard hat is actually your very last resort in the hierarchy of controls. We looked at the fire tetrahedron and why you should never throw water on an oil fire.
Because of the massive expansion and explosion.
And we explored the terrifying reality that just 6 to 10 milliamps of electricity can lock your muscles onto a live wire.
A let-go current.
The big takeaway for me is that the physical world has been painstakingly engineered to protect us, provided we actually pay attention to the signs.
It is an incredible testament to human ingenuity and our desire to protect one another. But this raises an important question. Everything we explored today focuses intensely on physical, chemical, and mechanical hazards. Nip points, falling objects, toxic gases.
The tangible stuff.
Right. However, the very nature of work is rapidly changing for millions of people. As we move further and further into virtual, remote, and AI-driven environments, how will these rigorous industrial safety principles apply to our cognitive and digital well-being?
That's a great point. We're not dodging falling wrenches at our desks.
Think about it through the lens of what we just learned. What does a lockout-tagout procedure look like to isolate us from the stored energy of a 247 digital workspace?
Unplugging the router.
Maybe. How do we measure the near misses of digital burnout before they compound into major psychological or occupational incidents? The hazards are shifting from physical gears to digital demands, but the need for a protective framework remains exactly the same.
That is a phenomenal thought to leave on. How do we build an ISO-certified safety culture for the mind? How do we put a dead man's switch on our email inboxes?
We need to figure that out.
Thank you so much for taking this deep dive with us today. We highly encourage you to take a look in your own surroundings right now. Whether you are walking past a construction site, cooking dinner in your kitchen, or just sitting in your office, and try looking at it through this brand new lens of hazards, risks, and engineered controls.
It's all around you.
Stay safe out there,
Yeah.
and we will catch you on the next one.